Okay, we're going to be doing lead code 560, Subarray Sum Equals K. First off, I just want to say that solving this in an optimal time is extremely tricky, and this is a question you can't do unless you know a certain mathematical principle related to prefix sums, right? It's not something that you the insight to this is a mathematical principle. It's not a programming pattern, right? Maybe this principle could later on turn into a mathematical pattern you realize in certain questions, right? But let's read the question and I explain to you. Given an array of integers called nums and an integer k, return the total number of subarrays whose sum equals to k. A subarray is a contiguous, non-empty sequence of elements within an array. So for this first example, we have 1, 1 and 1, right? So 1, 1, 1. There are two subarrays that equal to k, which is 2. Which two are these? This and this, right? Let's look at another example. 1, 2, 3. There are 2 which equal to k. This and this, right? So let's look at another thing here. The length isn't really an issue, but the numbers can include negatives, right? They can include negatives, right? So that means that we could have an array like this, say -1, 2, and these are not sorted as well. So -1, 2, 5, -3, 2, right? And let's say our k is let's say our k is 4, right? We can see that this would have been, but it's not, right? And this also is not, this is not, 5 and 3 is not, so this doesn't provide us any, right? But if we adjust the problem and then we have 5, we'll make this, hold on, we'll make this -1, and then we'll make 5, 2, 7, 8. We'll make this -3, right? So if it's like this, right? Forget these other ones that we did here. If it's like this, then how many subarrays? We have this subarray is equivalent to 4, and this is equivalent to 4. That's why we have 2, right? So let's first do the brute force to this is to simply find all subarrays, right? And the way we find all subarrays is we start at this position and iterate through from I onwards, right? We start from I at each position I, and then we go through j times from I onwards, right? Let me show you what that means. So this is the brute force solution, which takes n squared time, quadratic time, right? So we have our count is equal to 0. Then for I in range length of nums, we have a cumulative sum, right? Cumulative sum is equal to 0. Then for j in range length of nums, but we need to move from I onwards, right? Because if we start from if we start from j, then that's going to be way too many. So then we update our cum sum. It becomes cum sum plus equals nums at j. And then we check if the cum sum is equivalent to our k. So it will be if cumulative sum is equivalent to our k, we increment our count plus equals 1, our cumulative sum, and then we return count, right? So voila, that works, but it takes too long. It gives us a time limit exceeded error. So what is the optimal way of solving this, right? This is where you need a mathematical principle to help you, right? Time limit exceeded. The mathematical principle is, right, we're going to use this same array. -3, 2, 5, -1, 2, with our k equal to 4. The mathematical principle is, the mathematical formula is to find a subarray. You need to know, to find a subarray of size k in an array of integers negative to positive, right, is the prefix sum at j. So we have two pointers. We have two pointers, j somewhere in the front and I somewhere in the back, right? So the prefix sum, the Subarray sum, the number of Subarray sums, right, at point j is that are equal to k, right? The number of Subarray sums at point j that are equal to k in terms of the sum is prefix sum at j minus some other previous prefix sum at I. It will give us k, right? So using this, right, we can say prefix sum at j minus k will give us will equal to prefix sum at I, right? So for prefix sum at j, wherever there's a prefix sum that's equal to I, we know that we have a subarray of size k, right? So it's a tricky mathematical concept, but it's crucial to understanding this problem. So let me show you what I mean here, right? We're going to create a subarray. We're going to create another array below here, which contains the cumulative sum, right? And the cumulative sum starts from 0 outside here, and then -3. This will be -1. This will be 4. This will be 4 plus -1 is 3. 3 plus 2 will be 5, right? And our k is 4. So how do we find the subarrays of size 4? How do we find them? Well, we simply we go through at each position at 3 prefix. So our j is currently at this position, right? So prefix sum at j minus prefix sum at some point I that is behind us, right, will equal to k, right? So that means prefix sum at j minus k will give us the prefix sum at I. We need to look for here, right? So our I is somewhere behind here. But once we do this, we get the prefix sum that will ensure that this is correct, right? So we need to find the number of occurrences of this within this array of prefix sums. That's what will give us the subarrays of size 4. So here when we're at, so I'm going to code it out and then we'll write it out so that you can fully understand it, right? You're going to fully understand it once we code it out and then draw it up. Okay, actually let me leave, let me see. We're going to leave this as our example. So this is the linear time solution using n space, right? So we start by initializing a hash map with 0, right? So we'll call it occur. And what this hash map, right? This hash map stores the cumulative sum occurrences, right? So far, right? So as we're traversing through the array, we'll be storing the cumulative sum and its number of occurrences within the array. So we'll call it occur is equal to 0, 1. Why do we initialize with 0? Because our cumulative sum will start with 0, right? Despite the number of values in the array, starting from negatives, our cumulative sum starts from 0, right? So then we initialize a counter to store the number of subarrays of size k. So we'll call it count is equal to 0. And then we initialize our cumulative sum is equal to 0. And then we iterate through the array, collecting the cumulative sum and the number of occurrences of that cumulative sum, right? So we're going to say for num in nums, right? We update our cumulative sum, cum sum plus equals num. Then we check mathematically if there exists, we check mathematically for the prefix sum before, which if we subtracted from our current cum sum would equal to k, right? So let's call it so let's say here let me say cumulative sum minus cumulative sum before is equal to k. So cumulative sum before is equal to cumulative sum minus k, right? And then if cumulative sum before is in occur, right, is in our hash map, if the cumulative sum before is in our hash map, then it means we increase our count by the number of times it occurs, because if we subtract our cumulative sum with the cumulative sum before, for each occurrence of the latter, we get a subarray of size k, right? So every time previously we had a cumulative sum before, a cumulative sum equivalent to cumulative sum before, it means that between that occurrence and the current cumulative sum, we have a subarray of size k. So then we update our cumulative, we update our count, right? So count plus equals occur cum sum before, right? That's why the number of occurrences is what we return, because for each occurrence minus, cumulative sum minus each occurrence is a subarray of size k. Otherwise, we update our hash map with the cumulative sum. So if cumulative sum in hash map in occur, then occur at cumulative sum plus equals 1, else occur at cum sum is equal to 1, right? So this is how we fill our cumulative sum before, right? And this is how we find our current cumulative sum, right? So another way maybe of making this more clear would have been to do something like current cumulative sum and whatever, but that's why this is a tricky question, I won't even lie. So after we're done with this, we simply return the count, right? And voila, it works, right? So let's check it on the test case that we're going to be using, which is -3, 2, 5, -1, 2, and k of size 4. Let's run the code. You see, we have 2, right? We have 2 subarrays of size k. Let's try it with 2 and see. We have 2 as well, but let's trace it out, right? So for the trace, I'm going to take out some of this code, right? So that this stuff is clearer. Let me take out some of this code, because actually it's not a complex, the code isn't difficult, you know. The issue is actually with the mathematical logic behind it. That's where the issue is, not the mathematics. So we always need a cumulative sum before. That's why we initialize the hash map. So here we'll have our hash map with a cumulative sum, right? Okay, so we've initialized it 0 and 1, right? So in the code, let me make this a bit, okay. So in the code, we are at this point, right? That's what we just did in the drawing. So now we initialize a counter to store the number of subarrays of size k. So down below here, we're going to have our count. And then we initialize our cumulative sum with 0. So our cumulative sum is 0. Okay. So now we iterate through the array, collecting the cumulative sum and the number of occurrences of that cumulative sum, right? So we're putting them into our hash map. So we increment our cumulative sum, right? So here I'm just going to like put another array here too, but which doesn't exist, right? 0. So our cumulative sum was 0, but now it's if we look in the drawing, we are here. So what is our num? Our num is 3, is minus 3. I think let me add it somewhere here. Let me add num here so that we know where we are, right? So we'll have num here. So our num is negative 3, as you can see in the drawing. So our cumulative sum is, it's now going to be negative 3, right? So I'm going to update here. This is the cumulative sum array. And this is our original array, right? So now we come down here in the code, cumulative sum before. So I'm going to call it cum sum before, right? Cumulative sum before, in order to satisfy our subarray of size k, the cumulative sum before at this point has to have been cumulative sum minus k, right? Which is cum sum minus k. So what is our cumulative sum? Minus 3 minus 4, right? Which will give us minus 7, right? And now we check, is cumulative sum before in our hash map? No, it's not. So instead we update our hash map with our current cumulative sum, right? So it becomes negative 3. Since it's not, so it becomes 1, right? That's this code here is what we execute. And then we come back here to the next iteration. So our num is now 2, right? Our count is still 0. Our cumulative sum will be negative 1, which we update here, right? So our cumulative sum is now negative 1, right? We've updated it. So now the cumulative sum before, right, such that the cumulative is, in order to satisfy a subarray of size k, is going to be cumulative sum minus k. What is cumulative sum? It is negative 1. Hold on, this should have been here. Okay, so it is negative 1 minus 4, which gives us negative 5, right? Is negative 5 in the hash map? No, it's not. So we update our hash map with the cumulative sum, which will be negative 1. And the number of so we're executing this code, right? And 1. So we come back here for num in nums. So our cumulative sum will be, so our num is now 5, right? I made a mistake. This should have been a bit lower here. So our count is still 0. Our num is now 5. Our cumulative sum will be 5 plus negative 1. This will be 4. Our count is still 0. Then cumulative sum before will be the cumulative sum of 4 minus 4, which will give us 0. So if 0 occurs, if cumulative sum before exists in the hash map, And what's the cumulative sum before? It's 0, which we have here. Then we increment our count by the number of occurrences of the cumulative sum before, which is 1 in the hash map, right? So our count becomes, we increment it by 1. And this is because, let me first update our cumulative sum here, which I forgot. This because between here and here, there's one occurrence of the subarray of size k, which is 4. Why is this? It's because the cumulative sum at this position minus the cumulative sum before is equal to k. What is the cumulative sum at this position? It's 4 minus 0 is equal to 4, right? So that's how it works, right? So this is a tricky, this is a tricky thing to grasp your head around. You need to know the mathematical trick behind this, right? So after we're done with this, we update our cumulative sum. So our cumulative sum is 4, so we're executing this code here, right? So our cumulative sum here will be 4 and 1. Then we come back here. So in the drawing, you can see our num is now here. So our num is -1. Okay, here it was still 5, I guess. So now it's -1. Our cumulative sum is 3, right? Our cumulative sum will be 3. And then we've updated our cumulative sum. So our cumulative sum before, in order to equal k, will be cumulative sum minus k. Cumulative sum of 3 minus 4 will give us -1, right? So we check if -1 exists in the hash map. If you look here in the hash map, it does exist. Then we increment our count by the number of occurrences of this cumulative sum before. So our count becomes 2, right? And why does our count become 2? Because at this point, this cumulative sum here minus the cumulative sum at this position is equal to k, which means there's a subarray of size k here. And let me show you. 3 minus -1 is equal to 4, because 3 plus 1 is equal to 4. Right? The prefix sum at this position minus the prefix sum at this position is equal to k. Right? So we now update our cumulative sum in the hash map. So our cumulative sum will be executing this code, which will be 3 and 1. So we come back here, we push this here, our num is at 2, we update our num to 2, our cumulative sum, we update it, plus equals 2, which will give us 5, then cumulative sum before will be 5 minus k, 5 minus 4, which will be 1. Then if cumulative sum before is in the hash map, it's not, right? This 1 is not anywhere in the hash map. So then we update our cumulative sum by adding it to here, 5, 1. And then when we come out, we have our number of occurrences. The count of the subarrays is 2. So this is the solution, and as you can see, it is tricky. All right. So this is the solution, and this is a tricky problem. So thank you and bye.